Right, so
Hello, everyone. Today we are going to continue what we started last time. We started to talk about natural hazard risk analysis. We talked about hazard, exposure, vulnerability. We need to record this class, right? Did you guys check? Did I upload the recording from last time?
Yeah.
On campus? Or
not on campus.
okay. So was it clear or we need to be closer? Did you it wasn't uploaded. It wasn't uploaded. Oh. I think I forgot to put it on Canvas, but it's on YouTube. Okay, so last time we started talking about like let me put it here. Doesn't show the full. I'm sorry. Yeah, so we started talking about like hazard, exposure, vulnerability. And the thing is, why we are studying this to do something about it, right? We need to understand like, okay, my risk is like all my buildings are gonna get damaged. So what I'm gonna do, that's what I want to know. Do I need to do mitigation? Do I need to do adaptation? I need to understand my risk so that I can do something about it. That's what we need to do. So last time, for example, we, if you guys remember the community that we started talking about, we started talking about Lumberton, North Carolina, and then we modeled the hazard, the exposure, the vulnerability. And then at the end, once I use all these information so that I can predict the damage or the potential damage that is gonna happen to each building. When I say damage and potential damage, what I did in Lumberton, it was a real scenario, like it was flooding event happened after Hurricane Matthew. When I say potential damage, if we are studying a 100-year event, like if we have a hazard map for a 100-year event that it's gonna happen in the next 100 years. Maybe it's gonna happen today, maybe it's gonna happen tomorrow, but it's a 100-year event. That means a potential damage that might happen if a 100-year event hit the community. That's when I say damage and potential damage. All right, so we need to do something about these damage. What do you guys think emergency managers or community can use to mitigate the damage of these buildings? Do you guys have any idea about what communities can use to mitigate flood risk? What they can use? What is in your mind?
Sandbags.
Sandbags. So sandbags can help us what? Like can be a flood barrier, right? We can build a sandbags to be a flood barrier to protect a specific location. Can we put a sandbags for whole community like 3 kilometers? It's too much, right? So we can use sandbags at building. Like if you have your building, you can have 100 sandbags to protect your building, right? So sometimes we call sandbags, it's a building level mitigation that homeowners can use to at the lower locations of their house. Like you know that your garage is lower level than from your house. So you put sandbags at your garage so that your garage cannot get flooded. However, there's some like advances in the flood barriers. There's something it's called bladder dams. It works as a sandbags. It's like a plastic, a very thick plastic that like it's like a balloon and you fill it with water and it gets bigger and it can surround your whole house and protect your whole house. So that's called a bladder dam system. There's other systems that can be used like that bladder dam and like that sandbag system, maybe you can search it online. All these systems, we call it like building level mitigation measures. What else in your mind like that we can use to mitigate? I mean, like not real time, maybe we plan for the future, that a flood is gonna happen in the future, so we need to plan right now to do something about our community so that we mitigate flooding. Mitigation can include component level mitigation, building level mitigation, or community level mitigations. Do you guys have anything in mind? Dams like dikes or what we call them, yeah, like structures. That can, what do you guys know what dams do? Like exactly what dams do to protect us from flooding? So basically, our problem is, we don't have any problem with water flowing in a river, but sometimes this water get a maximum flow. So what we want to do, we want to regulate this maximum flow. So when the water is like this flow, my river can't handle it. But when the flow goes 10 times, we cannot handle it. So the dam protect this excessive flow from flooding in the downstream, so it block the water. And once you block the water is gonna back up, so it builds a lake behind this dam. So usually dams is built at areas that are at a lower elevation. So that because every dam builds a lake behind this dam. And then, once you block all the water, you can control the flow in the downstream. So you let the water with the flow that you want. So like you don't plug the water 100%, you kept it flowing, so it doesn't, like, let's say we have a dam and this dam is blocking the whole water, but the water is gonna, if the water reaches to a specific level, is gonna be dangerous to the dam and the dam gonna fail. So you let the water flow with a specific flow that doesn't damage the dam and also doesn't cause flooding in the downstream. However, sometimes extreme events is beyond the dam capacity, because the dam is built, I don't know, for 1,000-year event, but if you've got a 2,000 or a 10,000-year event, there's no way that you can do this. So dams also is still a structure, and we call these control structures. The structure is called retention systems. Retention systems is also like a dam, but it's like a big pond, like a lake or something at a lower elevation. You store the water in this lake and you let the water out of the lake with a specific flow that doesn't cause flooding in the downstream. We call these retention or detention systems, depends on if it's controlled or uncontrolled. Also, we have sometimes you can, like, let's say building on the beach, and every year the water goes up or the waves goes up and hit your building and your building get flooded. So what you do, you elevate your building. That's one thing. Also, let's say that you got a warning that there's a flooding is coming. What the first thing that you are gonna do? And like they say that your house is gonna get flooded next day. So what things that can save you money instantly? If you know that your house is gonna get flooded, do you have anything in mind?
I read something from the first floor to.
Like what?
So, like appliances or anything electrical.
That's true. Like you can move anything that is water sensitive to our elevation. Like if you have computers, if you have electronics, if you have any electronics that are very expensive and can be moved. Let's say that you have a second story, so you move all these in the second story. You take your car and put it on a higher elevation. So all these can save you maybe, I don't know, $10,000, $20,000, but it's still some savings that you can do. So all these are mitigation measures that you can use. So although all these mitigation measures are very good, but how we can capture this if we are doing loss estimates? So we need functions that can tell us if we did this, we are gonna save this amount of money, so that you can know if this is beneficial or not. So that's what mitigation analysis can tell us. So we are gonna take this from here and see how we can do mitigation analysis. So what we have been discussing right now is what mitigation options for the community can do, but we still don't know if these mitigation options are good or bad until we make mitigation analysis. So for mitigation analysis, this is the mitigation types, like some of you talked about sandbags. So some of you talked about moving water sensitive components on upper elevation. So all these are viable mitigation measures that communities can use. This is a framework that I published in one of my papers of how we take the fragility from quantifying damage to identify the impact of mitigation measures. Like, for example, this is a flow chart asking you if this building has a flood protection measure or not, like if it has sandbags, a water dam, if it has like sealed doors, a flood resistant walls, and then make some functions to capture the impact of these mitigation measures on the fragility functions. Because fragility functions is dealing with a building without mitigation. But what if we put a flood barrier around this building? So the flood fragility is gonna get different. What if we change it to component elevation? You guys remember that when we build the vulnerability function, it is based on the component elevation. Like if the TV is here, the fragility curve is gonna look like this. So what if you know that there's a flood is coming and you took this TV and put it on the upper elevation? So the fragility function of this TV is gonna be different. All right. So this is, for example, shows you actually one of the buildings that got exposed to flooding in Lumberton, North Carolina. This is Walmart in Lumberton. And if you can see, this is an aerial image. It shows how the water was surrounded around Walmart in Matthew 2016. So Walmart did something different in Florence 2018. They got some time and they built a flood barrier around this building. This is how the barrier looks like. Can you see? How's the water outside look like? So it's basically provided full protection of the water. And this barrier is around 1.5 meter height, 1 to 1.5 meter height. How we can capture this in the flood damage functions? So basically, if you have a building without any protection or without any flood barrier, it's gonna look like this. This is the damage function. If you've got 1 meter flood depth, you're gonna get 50% losses. But let's say you put a flood barrier of 1 meter or 1.5 meter height. So if you got a flood depth of 1 meter and you have a flood barrier more than 1 meter, so basically you're protected. There's 0 losses if this barrier works efficiently. So basically, as soon as the flood depth is less than the barrier height, all the flood losses are 0. Once the water depth exceed 1 meter height, this barrier is like useless. And then you will jump back to the same function that you had. So this is how we capture the impact of flood barriers on the damage. This shows you some pictures from actually like this is Lumberton during the Hurricane Florence. Shows you how they used pumps to take the water from the city to the riverside. And this is also the same picture, like a drone picture. If you see, this is the city side, and they are dropping it into the riverside. And also this is a picture shows you how the bladder dam look like, look how big it is. And they also use pumps just in case. First, they use pumps to fill the water inside the bladder dam. And some of them, like if you are using sandbags doesn't work efficiently sometimes. Sometimes it lets some water. So they use pumps to pump the water from inside to outside. So all these mitigations, that's household, like that's people, like they live in their houses and they try and mitigate the flood impacts. How can we capture the impact of flood duration? Since if you guys remember last time, we have a fragility surface that tell us what is the combined impact of flood depths and flood duration. So for example, we have here flood depths on x-axis and here's flood duration on y-axis. If they both increasing, they both increase the flood losses. So the flood losses reach 100% at the maximum flood depths and maximum flood duration. But let's say that you, like, for example, let's say at 1.4 meter and a flood duration of 24 hours. So you are going to be something like this. If you had 60 hours, it's going to be something like this. So if we were able to know what is the flood duration, we will be able to capture better damage estimates. But what if I don't have the flood duration? I have to assume the maximum duration. I have to assume that the water stayed there for a long time. So most of my analysis, if I don't have information about flood duration, I use the maximum curve, which is this curve, which is the 2D curve that we saw then last time. Like all this is based on maximum duration. I didn't consider flood duration when I developed depth fragility functions. All right, so this is the loss surface. The loss surface is just one surface, but if you guys remember the concept of fragility is an exceedance probability of a specific damage state. And we talked about that we have more than one damage state. We have slight, moderate, complete, extensive and complete. So each one of these surfaces represent a damage state. So if you cut a section in these fragilities, you will find that at one day, you will have these fragility surfaces. Damage state 4 is not there yet. Like you will not reach complete damage if the water stayed only one day, but then it's gonna show up as the number of days increased until the full function shows up after, for example, 10 days, and you are gonna get the full fragility curves for the entire building. We're gonna learn this in details when we come to the MATLAB and the fragility development, but I'm showing you a little bit of a brief of how the fragility functions looks at different flood durations based on the different sections that you took in the fragility surfaces. Here it shows the impact of elevating water sensitive components. Like let's say that this is your building and you were able to elevate the fridge, like not elevate the fridge to an upper elevation, but elevate the fridge, I don't know, like took the fridge and put it on a blocks, like a concrete blocks, or elevate all the computers, TVs, every water sensitive components. The furniture, you put them on an upper elevation, you get something and you put them on it. The thing is, as you see here, the blue curve is that if you don't have any elevation for the water sensitive component, the red curve, if you elevated the component, it's not that big difference, right? Like the maximum that you can do is that you can decrease the flood losses. Let's say that you got a flood depth, and actually it's different at each flood depth. Like let's say that you elevated all the components, and then you got only 2 inches of water inside your home. So basically, you are here, you basically, maybe you couldn't have elevated any component because the water is not gonna reach them, but you don't know, right? But if the water reaches, for example, 1.4 meter, which there's an optimum flood loss savings, you are saving almost 10%, which is, I don't know, like $10,000. Is it worth it? Maybe at the building level, you think it's not worth it, but if you accumulate this at the community level, like 1,000 building are gonna save 10,000, that's $10 million in savings. Okay, so sometimes you can use two mitigation measures at the same time. So here, for example, you're using sandbags, and at the same time, you are decreasing the flood duration by using pumps. So basically, I cut off the surface at 1 meter. So the flood loss is 0 if the flood depth is less than 1 meter. And if I'm able to decrease the flood duration by using pump, so rather than I'm using this curve, I'm gonna use this curve. This is also some mitigation measures at the community level. As I told you, you might build a flood barrier or a floodgate. So as you can see here, there's I built a floodgate at the intersection between a bridge and a railroad, and it provided full protection for this earth. However, when I did this in this piece of study, the thing is the water needs to go somewhere. You block the water is gonna accumulate behind the gate, and it's gonna go around the gate and overflow through the bridge and then or through the highway and flood your community. So I had to do another mitigation measure. I had to build a levee around the gate so the water cannot back up and go from a different place. And this is a retention system. Like I built a geometry here and I for a retention system. And when the water overflow here, the water comes from this channel and take the water to here as a retention system. It takes a lot of water from the river and then reduce the flooding in the downstream. So also this is one mitigation measure that I studied. However, this was very expensive to build. So it's all mitigation options. It depends what the community is going to do. And actually, when I read the reports about when this community is looking and what mitigation options that they want to do, they actually was looking and diverting the river. Like rather than making the river go through the center of the city, they are going to divert the river to go from the outside the city. That's also another expensive mitigation option. So the communities are looking for all the mitigation options that they can do to decrease the flood losses. But usually hazard mitigation measures are expensive. Like to build a levee or to build a floodgate or to build a retention system. Can you see here this black line? All this is a levee. I increased the elevation of this so it doesn't flood the road and it doesn't flood the street. So here it shows, for example, how when I built the gate here, I made a levee all around here just to retain the water behind this levee and protect around 1,900 buildings here. All these got full protection. However, the water is still backed up behind the levee and overflows some buildings that are around 50 buildings. But it's better that you deal with 50 buildings rather than dealing with 1,900 buildings. You can buy out them, you can provide them money so that they can increase their elevations. So sometimes one mitigation measure cannot work. You need to use a suite of mitigation measures, like use a levee, use maybe a small retention system, floodgate, and building elevation or buyout. So all these options you need to have in mind. Okay, with this, we are done with a single hazard risk analysis, just flood. What if I'm dealing with multi-hazard, like what happens here in Florida, dealing with hurricanes? You guys, what kind of hazards that hurricanes can bring to the communities? Anything in mind?
Extreme winds and storm surge,
Extreme wind, storm surge, what else?
flooding.
Storm surge is flooding, like storm surge is kind of, but yeah, if you are talking about the coastal flooding, that's the storm surge. It also can bring inland flooding, like can make rainfall flooding or marine flooding, what we call alluvial and fluvial flooding. Because it rains a lot inland, and when it rains a lot, it makes the like houses get flooded. What else? Waves. Waves is storm surge usually doesn't cause structural damage because it's a static flooding, unless if it goes with a high velocity. But what causes structural damage is that you have a high surge and waves on top of this surge. This waves like an impact force that can cause a structural damage to the building on the coastline. So the combined impact of storm surge and waves is also one of the hazards that can cause a structural damage. Do you have any idea what indirect hazards that hurricanes might bring? Hurricanes do a lot of things. Hurricanes do wind-borne debris, water-driven debris. They do wind rainfall intrusion. They do a lot of things. Indirect hazards, like you are away from the ocean. You are not gonna getting any surge. Maybe you are not getting a lot of wind, but you will get maybe some wind-borne debris from a communities that like adjacent to your community. Or there's rain and wind, and the wind is, you are gonna get wind-driven rain. So all these hazards that can be driven by hurricanes and cause damage. However, studying all these hazards one at a time is gonna make it very complicated. So usually researchers, they take it step by step. They study wind alone, or they study combined wind and storm surge, or storm surge and wave, or study just wind and wind-borne debris, or wind and wind rainfall intrusion. But there is still a lot of things that you can do as a researchers to find the combined impact of these hazards. All right, so let's dive in deep about what we can do in multi-hazard hurricanes. Let's focus right now on a storm surge, wave, and inundation like flood and wind speed. All these three hazards. So what we did with flood is that we have one hazard and overlay with the community and got the flood depth. So we're gonna do the same thing. We're gonna get all the hazard maps of all these four hazards or three hazards. Because I have here an inundation duration if I have it. So I have surge, wave, duration, and wind speed. I take all these raster maps, we call them raster maps of the hazard, and overlay them with the community in a GIS environment, and then identify the hazard intensity at each building. What is the surge height, the wave height, the flood duration, and the wind speed at each building? We can do this. We identify all the hazard intensity at each building, and then take them right now. Before, I used to have one single hazard, so I need one single fragility. Flood depths, I need flood depth fragility functions. Right now I have multi-hazard, so I need a set of fragility functions that can tell me what is the expected damage corresponding to each one of these hazards. Okay, like for example, some of these hazards can cause a structural damage, some of them can cause interior damage. But thing is, the combination is very complex. Sometimes we need to simplify it so that we can be able to solve it. Like, okay, storm surge causes interior damage, but doesn't cause much structural damage until it comes with wave with it. So storm surge and waves cause structural damage, right? And surge alone cause interior damage. And wind mostly causes structural damage. They damage the walls, they damage the roof, they damage the windows and doors. But you will tell me wind also causes interior damage. I will tell you if maybe something cascading impact, like a wind is gonna cause damage to the roof. You have a hole in the roof, then the water comes from the roof, cause your interior damage. So if you kept making it very complex, it's gonna take forever to solve. So we will assume, and that's what I did here, that wind causes exterior damage to the structure, like roof, walls, windows, and doors. Storm surge and waves cause two things. They cause structural damage to the foundation and the wall. And the storm surge and the flood inundation, that how much time the surge is gonna stay there, is gonna cause interior damage to the interior components. Are we agree on this? So that's a good assumption. So you will tell me, but you neglected the wind rainfall intrusion and the windborne debris and the wind drip and the water driven debris. Sometimes we have to neglect things so that we can like solve the problem. And then once we solve it, we put the limitation of the study. This is for buildings that are exposed to 1, 2, 3. Okay, all right. So this is the set of fragilities that we have to quantify the damage. I have a flood depth duration fragility function that can tell me what is the content damage driven by storm surge and flood duration. And I have a wind fragility that can tell me if this building got hit with 100-mile wind speed, this is the amount of damage that is expected. And I have a surge wave fragility that can tell me the structural damage that can be driven by the storm surge and waves. And then I can combine the 3 damages together and come up with what is the total damage that can happen to this building. So that's how we do multi-hazard hurricane damage assessment. So for hazard modeling, so we have here, this approach was applied to many communities. I applied this approach to Waveland, Mississippi using Hurricane Katrina in 2005. Was applied to Galveston, Texas using Hurricane Ike in 2008, and also Mexico Beach, Florida using Hurricane Michael 2018. So it has been applied to many communities and has been published also if you want to look at the publications. So right now we are focusing a completely different test bed or a community. So I was looking at the impact of Hurricane Florence in 2018 on the coastal region of the entire state of North Carolina. So this shows you the how's the hurricane bath look like. This is actually a part of an ATSER and SWAT simulation. So here's it shows the storm surge map and the wave hazard map and the wind hazard map. So, and that's actually makes sense because I want you to look at the wave hazard map. So if you see the high waves is about 7.5 meter and it's usually in blue. And that's actually just maybe 1 mile from the beach, right? When you go outside of the beach, 1 mile, there's not much waves, right? So you'll find that the colors start to be yellow and red, which is almost 0.1, 0.5 meter height waves. But the storm surge can goes inside the land, very, very inside. It's gonna go inside and fill all the channels and overflow these channels and make flooding, and can't be something like this. So that's how the storm surge look like. The wind, basically, if a wind hit a coastal estate, the coastal estate is gonna, the whole estate can feel this wind. But the areas that are close to the ocean is gonna feel it more. So the hurricane hit that way. So the blue color area is where the area that got exposed to a lot of wind. However, you are gonna feel wind, maybe if you are here, but is this wind enough to make damage? No. So like, let's say that you have a fragility functions that can capture the wind damage. So let's say that you have a wind 50 miles per hour. What is the probability of exceeding damage state 1 or 2 or 3? All of them are 0. When you will start to see damage, when the wind speed exceeds, I don't know, 50 miles per hour. Okay, so what I did here, rather than looking at the entire state, I tried to find a threshold of a wind speed that I can not like that I can consider wind damage in. So this is, for example, 50 mile or 70 mile per hour. I made a line here, and I'm only focusing on the wind damage in this area because I know all the buildings here, they are gonna feel wind, but the wind is not strong enough to cause damage because it's below 50 mile per hour. However, I'm gonna focus on this area. All right, so the next thing is to hazard is the exposure modeling or the community and exposure modeling. So let's do community modeling first. If you guys remember last time, we developed archetypes to model the different building occupancies within the community, and we have a fragility function for each one of these archetypes. But right now we have multiple fragility functions: wind, storm surge and wave, and flooding. So what we are going to do, each one of these fragility functions, they need archetypes to model them. You need wind archetypes, you need surge wave archetypes, you need flood archetypes. Why? Because each archetype is going to have different surge wave fragility function, different wind fragility function. And we talked last time that wind has different impact from flooding. Like roof shape is very sensitive when we do damage analysis, but roof shape is not sensitive when we do flood damage analysis. Foundation type or foundation elevation is sensitive when it comes to flood damage, but it's not that much sensitive when it comes to wind damage. So every hazard is going to have its own archetype. So we need to get the archetypes corresponding to each hazard and assign them to the community. So here I assign flood archetypes, and here I assign wind archetypes. There's a paper that has 19 wind archetypes. I assign these archetypes here and assign these archetypes here. So then the next step is to overlay the hazard map with the community map, and so that we can identify what is the hazard's intensity at each one of these buildings. For example, we need to find what is the storm surge height at each one of these buildings. Same thing about the wind speed at each building. But here's an interesting thing. Like right now we have multiple zones are exposed to different hazards. Look at this. This zone, this line, do you guys remember when I made a line to isolate the buildings that are exposed to a damageable wind speed? So all this area is exposed to wind speed and significant waves height and storm surge. So exposed to the three parts. This area is not exposed to much wave or a damaging wave, but exposed to storm surge and wind. This area is exposed to wind only. This area is exposed to storm surge and wave without wind, or with wind, but this wind is not damaging. This area is only exposed to surge only. Do you guys understand this? Right now we got with multiple exposure zones, and each zone require different way that we deal with damage. So here we are going to find combined damage from a storm surge, wave, and wind. Here, just damage from wind. Maybe you will find tiles moving from the roof, but there's no water. Here, there is just the storm surge and wind, so we need each one use different functions. But when I did the analysis, rather than dividing it to much zones, and each zones I developed separate function, I tried to like list every building and see what hazard it's exposed to. And let's say if a building has a wind speed of 120 miles per hour, storm surge of 2 meters, a wave height of 1.5 meters. I take all these hazards and go in the fragility functions and let the fragility functions do the math, and they'll tell me, oh, this building is going to have this damage in wind, this damage in storm surge, this damage in the flood duration and the flood depth. So I use the 3 fragility functions to do the damage, but it's better to understand what each building is exposed to. All right, so vulnerability modeling, as I told you, that's what I did. So I took the storm surge and used the fragility function to do the interior content damage, because water is going to cause content damage. But combined water and wave is going to cause a structural damage that comes from the combined impact of storm surge and wave. And wind can cause like the wind structural damage. So this shows structural damage. This shows the interior damage. And I have some damage state that describe each one of these, so I can know if each damage state is exceeded or not. Then I have a set of fragility function that can tell me what is the damage state from the surge and wave? What is the damage state from the wind? What is the damage state from the flooding? And based on these damage state, I can get one single damage state for the entire building. And same thing for the losses, and I have 5 variables. These 5 variables are where the wind speed, storm surge height, significant wave height, building elevation, and flood elevation. This is the 5 variables. So the losses as a function in the 5 variables, I get first the storm surge losses, the wind losses, the flood losses, and I sum all of them together to get the total building losses. But this just for one building. If I want to do this for an entire community, I have to develop an algorithm that can read all the buildings data, all the hazards data, and then go do it like here. Yeah. I can read all of these informations and then I calculate the hazard intensities and then use the surge wave fragility, flood and wind fragility. And for building one, we run all these functions, the exceedance probability of each damage state. And then after I'm done, go again to building number 2 and run the same loop and building 3, building 4 until I finish all buildings. So this is the final analysis that shows how the building damage look like. So here's, for example, you will not be able to see here. That's why I take some close-up view. For this, okay, so I have this area here, and here's I'm showing how's the flood damage in terms of damage state look like. And then I'm showing the wind damage. The wind damage is 0, like there's no wind damages here. And here the surge wave damage looks something like this. And right now I have the 3 of them. For structural loss, I have the percentage of the structural losses for the same neighborhood and the content loss. And the total loss and the total damage. What is the difference between losses and damage? Losses is in terms of money. Like, let's say that you have 41% losses. If this building is $1 million, you lost $410,000. Total damage is a damage state, like is your building is a slightly, moderately, or extensively, or completely damaged. So that you can have an idea how your building is gonna look like if it got hit with Hurricane Florence. With this, I wanna show you like some research ideas when it comes to community resilience analysis. So all what we have done so far is identifying the damage, right? We talked about some mitigation measures. And then we talked about this mitigation measure is gonna how to protect your building, right? So we are building a flood barrier or we're building whatever so that your building gets, I don't know, like maybe reducing the damage from 40% to 20% or from 40% to 0%. But I believe I talked about this last time. Let's say that you elevated your building and the flood hit your community and you got 0 flooding inside your house and you protected your house. But what if the place that you work at is damaged and the gas station that you fill the gas at is damaged and the hospital that you go to is damaged and the school that you send your kids to is damaged? Are you gonna be able to live in your building? I believe maybe not, because there's nothing that you can do. You can't work, you can't do anything. So it takes us to a different definition or different terminology that maybe we are not interested that much in damage, but we are interested in functionality. Maybe you are not damaged as a building, but you are not functional as a system. Same thing, let's say that everything is functional. Schools are functional, hospitals, your work is like the workplace that it got flooded, and your house is not damaged, but the power substation got flooded and the water treatment plant got flooded. You lost access to water, you lost access to power. There's no power, there's no water in your house. That's not a livable house. You can't live in a house without water and power. So that also takes us from damage to functionality. Do you guys understand the difference? Functionality is how like operable you are inside your home. Damage is like physical damage that happens to your property. So how we can solve this? Same thing actually happens, maybe there's power, there's water, but there's flood around your house, you can't move. You can't take your car anywhere. So transportation network also affect your home. And even cell phones. Like if you live in a house that doesn't have any access to cell services, maybe you decide to leave your house. I'm not sure. Maybe you guys tell me, if you live in an apartment that doesn't have any cell service, would you live in this apartment? Maybe not. Even you have water, you have power, you have everything, but you have to drive 10 miles away to go to the hospital and you are okay with that, or 5 miles away to go to your workplace because you have a cheap rent, but there's no cell service. I don't believe that anyone would live in a place that doesn't have cell services. Even maybe, I don't know, 30 years ago, it was something else. But right now, everyone is depending on the cell phone services. You can take on this gas network, sewer network, every network that you can imagine important to your functionality. So that's why right now we are gonna talk about community resilience analysis. And when we talk about community resilience analysis, it's beyond building level and it's beyond damage. Okay, so for community resilience, it depends on three things: the household, the building, and the networks. Depends on the household itself, like the people that live inside the house, and the building itself, how it's functional, and the networks. I mean, buildings, I mean all the buildings in the community, residential, commercial, social institutions, the schools, the hospitals, all this matter. And networks, water, power, transportation, cell, and everything. So all these three things depend on each other. Households depends on building. You depend on your house to live in. You depend on the hospital to get health care. You depend on schools to get educational services. You depend on gas stations, retail. All this affects your functionality, and all of them are interconnected together. And if you want to do resilience analysis, you want to understand the relationship between them. There is extensive research that they study the interdependencies between buildings and schools, buildings and hospitals. Okay. And the second thing is the network. So all of them are connected together. Households use networks to get to buildings, and buildings use networks to be functional. They use water and power to be functional. And people use transportation to get to buildings. It's kind of a very complex interdependencies between the three components of the community. Communities cannot be anything or cannot get you anywhere without these three interconnected and like operable together. So when we need to study community resilience, we need to focus on these three things. And this is kind of shows you how they are dependent on each other. Like, look at this. So here, this is the network. You have the power network. The power network feeds the water network. You have a pump station. The pump needs power. And you have water treatment plant needs power. You have sewer needs power. So all the power network feeds the water network. So the next thing is the transportation network. Transportation networks also depends on the power. Can you tell me how? Traffic signals, right? So traffic signals operable on. So if the traffic signals are all, you are going to have a lot of crashes. Okay, so all these are interdependent on each other. This is interdependent on this or on this. And buildings, you have multiple sectors. You have residential, commercial, social, and all of them, they need power, they need water, they need accessibility. So all of them are cross-dependent on each other, okay? And then you have the household. The household has multiple levels. Like you have in your household, you have people that work, you have kids that go to schools, you have patients that needs healthcare. So the households provide labor and also provide students and patients to like healthcare and educational services. And the labor provides staff for commercial services, for social institutions, teachers, doctors, and the same thing for the residential sector. So it's all dependent on each other. If you were able to solve these interdependencies and cross-dependencies between the three systems, you are going to get somewhere in solving the community resilience analysis system. So the thing is, our approach to look at this, do you guys have any idea how we can link them together? how we can link people to buildings and to networks. Do you have any ideas? Like, I know we are structural engineers and we only like sometimes focus on buildings, but there's urban planners. They mostly this work is urban planning work. However, civil engineers start to get more in this work because also civil engineers, I'm not talking about structural engineers, civil engineers, they also do planning. Who build the infrastructure, transportation, water network, and all of these is built by civil engineers. So if we need to think about this as a civil engineers, we can do this. Like, okay, let's say that we have a building and I have a map of all the buildings within the community. And same thing, I have a map of the transportation network. And I have a map of the power network. Where's the power lines? Where's same thing with the water network. I have a map with the water line. Somehow I can link every building to a node on the network. Like, let's say I have this building. I will try by an algorithm to connect this building to any node on this network, like this closed node. Can you see like here? You see this is the blue one is the water network. Here. So if you see the power network is the water network is like going like this, and there's a neighborhood. So there's a link here, and you go here, and there's a link here. Then the water line, it goes inside this block so that it can feeds water to each building, right? So there's an algorithm that we can develop and link every building with every point on the network. Same thing with the transportation network. We can link every building with every point on the transportation network. And we connected buildings with networks, right? Have buildings and we have postmaps and we did some GIS analysis to link them together. The second level is that I want to link people or household with buildings, right? So there's something called census data. Census data provides you information about the household that lives inside buildings. So somehow we can use algorithms that can tell us, that can use the census data to map household to each building. Basically, census data doesn't tell you who lives where, because that's like you infringe the privacy of the people. So, but it tells you this whole block has 500 people live in it. Okay, but doesn't tell you who lives in each building and who lives in each housing unit. But urban planners, they developed algorithms that can map these 500 to these buildings. Like they developed something called synthetic allocation algorithms. And by the way, census data, it doesn't tell you only the number, but it tells you what are the races. Like these 500 is like, some is white, some is Asian, some is this, some is this. So it tells you what also the income group of each, like it tells you that 100 of these, they make around $100,000. Another 100, they make $40,000 to $50,000 or something. So it tells you a lot of information. So urban planners developed the mapping algorithms, and these mapping algorithms, they map household to each building. So right now, we connected households with buildings, right? And then connected buildings with nodes to the network. So this is how we connected the whole community together. So if you know a flood happened here and this building or this area got flooded at this side. So you know that there's no accessibility here to the transportation network. And you know that this household got flooded, so it might get dislocated. And if you know that the water treatment plant that feed this water line got damaged, so you know that there is no water in this area. So this is how we can capture not only the damage, but we can know if the transportation network is working or not, or if the power is working or not, or if the water is working or not. So we can do all this so that we can find out what is the functionality of the buildings. This is an example of the allocation algorithms that one of my colleagues in Texas A&M universities developed that allocate, like, for example, this is the schools. the location of the schools. And this is shows you where the students that live and where's the school at and how they go to schools. So all these students that goes to these schools and all these students go to these schools. That's what we call allocation algorithm. To allocate households to building, allocated students to schools, allocated staff to hospitals, allocate patients to hospitals. So this is kind of shows you how, like, this is the staff of these schools, where they live, and this is the school that they go at. This is an example of population allocation algorithm. It tells you where is the people live most. So the blue areas where most people live. But the thing is, to do community level resilience analysis, you need extensive data. You need extensive data about the household. You need extensive data about each residential sector and each social sector and commercial sector. You need information about the network, right? If you don't have then the water network, you will not be able to connect buildings to power or water. So you need all of these data. Because it shows you, for example, for network, you need the topology of the network, the connectivity of the network, the capacity of the network, like if it's 2-lane or 3-lane or 4 lanes, the dependency of the networks, where it gets power from, where they are dependent on each other, and what is the service area of each network, where it's served. So you need all these informations about the network. Same thing, if you have a school, I will not be able to do students allocation to schools without knowing the school capacity. If the school capacity big, 500 students, I can't allocate 1,000 students. I only allocate 500 students. So you need to know school type, if it's elementary, middle, high school, the school capacity, the school location, and the building value when it comes to damage. Same thing with the hospitals, the capacity of the hospital, how many beds that the hospital can have. So all this information you need so that you do all this analysis. So usually, we can do this research alone. We need a lot of people to work with us. Engineers, maybe they would be able to do damage, maybe would be able to link some models together, but you need a social scientist to do this for you. You need an engineer expert in infrastructure to do this for you, and somehow you all figure out how to link all these together. This is like the approach or a proposed approach, like, okay, like, professor, you told me that I need to know if the building is damaged or not, if there's power, water, transportation. How can I find a functionality? Like, is the functionality dependent on one of them or all of them? And if it's all of them, how? So we need somehow to find an equation or something that can describe the functionality of a specific building, right? Somehow we need to find this. So what we did is, we said, like, let's assume that the functionality of a building is omega. And this omega depends on many omegas. One of the omegas is the physical functionality of the building, if the building is physically damaged or not. The second one is the power. The third one is the water. Another one is the transportation. Another one is the schools. Another one. So you can keep including systems as much as you can up to any systems, but be like careful, because the more system that you add, the more that you make your system more complex. Okay. So we come up with something is called functionality vector. This functionality vector can describe the functionality of your building. This vector has every information that you need so that you can judge the functionality of a building. But we still didn't do something like, you provide me a vector that has 10 numbers. I only need one number that to tell me if this building functional or not functional, or tell me this building is functional 50% or 20%, right? That's what engineers would like. They need to know, I can live in this house or I can't, or tell me how much functionality is this building at. So to do this, you have to find what is the most important for you. Like for me, maybe I would live in my house and my kids go to school for 1 or 2 weeks. And maybe my kids, hopefully they are gonna be not sick. I might not leave the hospital now, and if I need it, I'm gonna drive 10 miles to drive the kids to the hospital. And you will tell me, maybe I can't live with water. Water, I can like go and buy some water tank and live on a water tank for like a week, right? So it depends on you, what you can tolerate. There's some families they can't tolerate losing any of these. Okay, so that's what the community or what the household can decide, and we can have a percentage of the importance of each one to you. And all of them, they are gonna make the 100% functionality that you need. And if you lose one of them, you lose from this 100%. Let's say, definitely you can live in the building if it's damaged, or extensively damaged. So that's basically maybe 50% of your functionality. And the other 50, maybe another 10 for the power, or 15, another 10 for the water, another 5 for the transportation, maybe another 10 for the schools and network. So here you decide what is most important to you. And if you come up with what is most important to you, we can do some analysis that can tell you what is the total functionality of your house. If you were able to come up with what is the functionality weight of each one of these systems. And also we can do it probabilistically, like let's say everyone is different. Like we can say that the functionality depends like 50% on a physical damage. Maybe the mean is 50%, but there's a standard deviation of 0.1 of this. Everyone has different tolerance. Let's say that you don't need water that much. Let's say you decided to say that the water contribute to 5% of your functionality, but maybe somebody else depends more on water, and other one depends less on water. So you can make it probabilistic and say there's a standard deviation. Some people will need it more, some people will need it less. And then we come up with what is the probability of exceedance of each functionality states depends on each system. That's system 1, system 2, system 3, and each system is going to be multiplied by a specific weights. All right. So this, I'm not going to get much into math, but I'm just giving you some ideas about how we can, at the end of the day, know what is the functionality of a specific building. Do you guys follow with me what I'm doing here? Is it that I know it's a lot of research here, but I'm just showing you what is the research trend at. Because at some point there's some people, some stakeholders, they want to make decisions like policymakers, governor, emergency managers. And when it comes to these people, they don't look at a specific single building. They look at the entire community. And at the end of the day, they are not going to care about each single house because they have power, water, transportation. They want one single number of the entire community, where our community at a functionality. Our whole community is 50% functionality, 20% functionality. How can I increase this number? To increase this number, you need to look at each network, you need to look at each building. So what we are trying to do, we are trying to solve the problem at the building level and take it to the community level so the stakeholders and policymakers can make decisions. All right. Okay, so the last thing that I have today is the recovery, which is a very important part of natural hazards and the disasters. So I'm not saying natural disaster, I'm saying disasters, because disasters are not natural. So for example, hurricane hit and your community got damaged. A few days later, you want to get recovered. What do you think the most important factors that help in the recovery process? I know that not all of you experienced hurricanes, but maybe some of you. But what things that we can do that can make the whole community recover from a hurricane? Do you guys remember Hurricane Ian that hit Fort Myers in 2022? Hurricane Milton, Helene, like a few months ago last year. So people got flooded, but how makes the community that got flooded and the houses and the businesses recover and come up to 100% functionality? What do you think things that the community need to do so that the whole community can recover back? First, you need to clean the roads, right? All the debris, everyone, like I have been part of Hurricane Ian reconnaissance. So the first thing that people do, they clean their houses, like the electronics that got flooded, the furniture that got flooded, and they start cutting the dry walls that got flooded, and they start rebuilding their homes, right? So the very thing, you have all the things that are damaged out, and then the trash trucks, they come and pick it up. So you need cleaning.
The next part, you need permitting. You need like to do new construction work. You need to get permits. And the sooner that you get permits, the sooner that you are gonna get recovered. So if we like this process is fast, you are gonna get recovered faster. But the thing is, I told you about this last time. Maybe you are working so hard in your house to recover, but the county or the city, they need to work hard on the water to get recovered, on the transportation to get recovered, on every network to get recovered. Schools, hospitals, your work, gas stations, all these need to get recovered. So looking at the recovery process, it's a very complex, you have to look at many things, but let's focus on one thing, on the recovery process of a house, like just fixing your house. So you can't looking at the recovery of just one single system, or you can't look at the recovery of the entire community, but you cannot do the community without the system. So this is what we call the recovery curve. It's basically a functionality over time, right? We talk about functionality, but we talk about functionality just post hazard. Hazard hit, what drops you down? What drops me down? I don't have power, I don't have water, my building is damaged, I don't have accessibility, all this dropped me down. So what we looked at is functionality at a specific time, but what we are gonna do right now, we are gonna look at the functionality over time, maybe over 1 or 2 years. That's what we call the community resilience curve or the recovery curve. Let's say 100 days before the hurricane hit, you're building at a 90% functionality. Maybe you need to fix some stuff in your house. Your roof needs to be replaced because it's under the code and you need to bring it up to the code. So you work it on your house very hard to bring it to 100% functionality. And then hurricane hit or a flood hit, what happened? Your whole functionality dropped. How it dropped? I don't know. Damage, no water, no power, everything. So you dropped it from 100% to 40%. That's what we call post-hazard functionality. Here, when you were at 90% and you went to 100%, we call this preparedness. That you prepare your house for the next event. That was the preparedness, and then a hurricane hit, you had a loss of functionality, and you came down here. So, and then 2 days later, you clean, and then you want to do the recovery. The recovery is usually hit by a delay. It takes a few days, maybe a few weeks, until everyone is different. Like some people, I'm not gonna recover now. Maybe I will get hit with another hurricane. You guys was following up the news. Hilton and Helene, who happened for Milton and Helene. They happened back to back. People that got flooded from one, they got flooded from the next one. So maybe people, oh, I'm gonna do the recovery after the hurricane season. So, and some people will decide now, but they will still have with delay. They need permits, they need a lot of things. So there's a lot of delay in the process. And then you are gonna start the recovery, and the recovery takes a lot of time to rebuild your house, and they can rebuild their network, their water, their transportation. And then you are gonna have the repair, and then you bring back your building to the 100% functionality. That's what we call the recovery curve. This is a very, very important curve in community resilience planning. So this is just have it in your mind. What is an x-axis? Is the time. What is the y-axis? The functionality. The functionality over time is the recovery of a building, and it's usually a step function, and then you have the recovery curve. Well, I hope that this was an interesting topic. We have been talking for 2 lectures, but what I'm showing you right now, we're not going to do all this stuff. We're mostly focusing on risk and damage. But I'm telling you how you can take this class to the next level and look at community resilience analysis, because it's very important. And working in this field is very interesting. One day when I graduated, I was doing my master's, I was passionate about buildings, and I want to be a structural engineer. I want to design tall buildings and 100-story buildings and everything. And I like this, like I love it. But also this is an interesting career, and I'm sure it has a lot of money, especially here in the US. If you got to be an expert in this stuff, you are shifting your salary to a completely different level when you get to the expert level. Like as a structural engineer in companies, I don't know, maybe you start with $80,000 a year,
And maybe when you become 10 years experience, your salary is gonna be, I don't know, 120, 130. And if you work in forensic or something, maybe you will get to $200,000 per year when you like very expert with 20 or 30 years of experience. But this field, I know friends, they got my friends, they got their PhD in this stuff, and they got salary 150 per year just to start. And then they are making right now with 5 years or experience, they are making over 200 years, working for insurance companies, working for risk modeling companies like RMS, working for Munich Re, for a lot of insurance companies from this work. So if you got expert in this work, but to be expert in this work, you have to be a civil engineer and you have the basics of risk and reliability. And this class is the first step to do this. So right now we are done with the presentation stuff. Next lecture, everything's gonna be on the board. We are gonna like start to understand the basics of probability and statistics, and then reliability. We're gonna do this for like a month or a month and a half. And then we are gonna do applications. Okay, so it's gonna get a little bit difficult. I'm not sure how difficult to you, but it's, if you like statistics, it's gonna be a piece of cake. If you don't like statistics, it's gonna be a little bit hard. I'll try to make it as much simple as I can, but you need to work on yourself. You need to go review your basics on statistics. I'm gonna explain everything. You don't have to have any background, maybe a little bit it can help you, but I'm gonna explain everything. And then the applications, as I told you, you need to get yourself good in MATLAB, because there was hundreds of lines of MATLABs ahead of you to write. So, but I'm gonna provide most of the coding here on video, so you'll see what the codes that you need to write, but you need to understand MATLAB very well, okay? All right, that's good. See you guys next time.